Welcome to Two Projects. In this video, we are going to explain the project Detection of Apple Plant Diseases using leaf images through Convolutional Neural Network. Introduction. Agribusiness has been a fundamental source of nourishment for decades, providing nourishment to approximately half of the global population. As the global population grows, there is an urgent need to increase agricultural production by 50 to 60% to ensure food security, especially in countries experiencing rapid population growth. The cultivation of apple crops, a widely consumed fruit globally, faces challenges in proportionally increasing production with the expanding cultivation area. In India, for instance, while the apple cultivation area has grown by 20%, production has only seen a marginal increase of 1 to 2% over the last decade. And globally, pests and diseases pose significant threats to apple crop production. In India, fungal diseases, particularly in Himachal Pradesh, a major apple producing state, adversely affect fruit quality. Biotic diseases caused by pathogens like viruses, fungi, and bacteria are highly transmissible and pose a substantial risk to both leaves and fruits. So, the project aims to address apple crop challenges through a diverse approach. Multiple deep learning models, including pre trained ones, are built for classification, and YOLO series models are employed for efficient disease detection. Leveraging image processing and AI, the project ensures timely and accurate disease diagnosis. And the significance of this project lies in its potential to revolutionize disease detection in apple plants, contributing to global food security. By employing state of the art models, the project aims to provide farmers with a tool that can quickly and accurately identify diseases, allowing for prompt intervention. And the beneficiaries of this project include farmers who can safeguard their crops more effectively, ensuring increased yields and overall food security for the growing global population. Objective of the project. So, as I mentioned earlier, the objective is to develop and implement an advanced system leveraging deep learning models to revolutionize the identification of diseases in apple plants, particularly focusing on scab, black rot, and cedar rust in apple leaves, ensuring early and accurate detection for effective intervention and enhanced crop yield. And we aim to implement algorithms and techniques to enhance the accuracy of disease detection, ensuring reliable and precise identification of specific issues affecting apple crops. And the aim is to provide a practical tool for farmers by delivering accurate disease identification, empowering them to make informed decisions to safeguard their apple crops and enhance overall agricultural productivity. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of law of work. So the first step is import and required packages. So in this initial phase, essential Python libraries and packages are imported to facilitate subsequent data processing, exploration, and model development. These libraries include those for data manipulation like pandas and numpy, image processing tools like sklearn, and for machine learning frameworks like sklearn and TensorFlow. The next step is exploring the dataset. So the dataset sourced from Plant Village for apple leaf disease and apple leaf detection from RoboFlow is explored to understand its structure and contents in this step. This step involves analyzing the types of images, their labels, and any additional information that aids in the subsequent pre-processing and training phases. The third step is image pre-processing. So here, utilizing the image data generator from Keras, images are pre-processed to enhance the model's ability to generalize. This involves rescaling the images to a standard size, applying shared transformations, zooming, horizontal flipping, and reshaping. Additionally, Torch vision based processing is implemented specifically for the detection models to optimize the input for the YOLO series. The next step is training and building the model. So, multiple classification models including VGG19, ResNet 152, DenseNet 201, MobileNet V2, ResNet 50, VGG16, Inception V3, Exception, MobileNet, and a custom Deep CNN are trained on the pre-processed dataset. Each model aims to classify images into categories corresponding to different apple leaf diseases. And for detection tasks, YOLO models, that is YOLO V5, YOLO V6, YOLO V7, and YOLO V8, are trained to identify and locate objects within the images. This step is crucial for recognizing the presence and extent of diseases in apple leaves. And as an extension to the project, a user friendly frontend is created using the Flask framework. And the frontend incorporates user authentication with SQLite for sign up and sign in. So, after signing in, users input images that undergo pre processing, and the trained classification and detection models are employed to provide outcomes, which are then displayed through the front end. So, this extension enables user testing, enhancing the practical applicability of the developed models. Now we'll understand about the algorithms used. So first we'll see the classification algorithms. The first one is VGG19, that is Visual Geometry Group 19. So VGG19, a convolutional neural network, employs a straightforward yet effective architecture with 19 layers. It stands out for its simplicity, utilizing 3 by 3 convolutional filters extensively. In this project, VGG19 is chosen for its ability to learn complex patterns, making it suitable for the nuanced task of classifying diseases in apple leaves. The next algorithm built is ResNet 152, that is residual network with 152 layers. So ResNet 152 introduces a breakthrough concept of residual connections, allowing direct information flow between layers. This mitigates the vanishing gradient problem in deep networks. With its depth and focus on capturing intricate features, ResNet 152 is pivotal in classifying diseases in apple leaves, especially when dealing with complex patterns. The next one is DenseNet 201, that is densely connected convolutional networks with 201 layers. So DenseNet 201 revolutionizes network architecture by densely connecting layers in a feed-forward manner, promoting feature reuse. This design enhances feature propagation and resolution learning. For the project's image classification task, DenseNet 201 is chosen for its efficiency in parameter utilization and robust feature learning. The next algorithm built is MobileNet V2. So MobileNet V2 is designed for efficiency on mobile and edge devices. It employs depth-wise separable convolutions, reducing computational load while maintaining expressive power. In this project, MobileNet V2 is chosen for its lightweight architecture, making it suitable for real-time disease identification in apple leaves. The next one is ResNet 50. So ResNet 50, a variant of ResNet, strikes a balance between depth and computational efficiency with 50 layers. Residual connections enable efficient training. Its immediate depth and computational efficiency make ResNet 50 suitable for image classification tasks, including the identification of diseases in apple leaves. The next algorithm used is VGG16. Similar to VGG19 but with 16 layers, VGG16 employs simple convolutional filters for hierarchical feature learning. Its balance between simplicity and performance makes it a valuable choice in the project for image classification tasks, providing a pragmatic compromise. The next one is Inception V3. So Inception V3 stands out for its Inception modules utilizing parallel filters of varying sizes to efficiently capture features at different scales. With reduced computational load, Inception V3 excels in handling diverse features in image classification, making it a prudent choice for the project. The next algorithm built is Exception. So, Exception introduces depth-wise separable convolutions, improving information flow and computational efficiency. Selected for its effectiveness, Exception is employed in the project to leverage its efficient architecture for image classification tasks, particularly when computational resources are constrained. The next algorithm built is MobileNet. So, it is designed for mobile devices. So MobileNet utilizes depth-wise separable convolutions and efficient channel factorization. With a focus on efficiency, MobileNet is chosen for the project to ensure real-time applications on devices with limited computational resources. And the next one is Deep CNN, that is Deep Convolutional Neural Network. So Deep CNN is tailored to the project's specific requirements, incorporating convolutional layers, pooling layers, and fully connected layers. This flexibility allows the model to adapt to the unique characteristics of the dataset and the task at hand, ensuring solution for disease classification in apple leaves. So now we'll discuss about the algorithms used for detection. So we have used YOLO V5, YOLO V6, YOLO V7, and YOLO V8. So YOLO, that is You Only Look Once, is a real-time object detection algorithm, uniquely divides an image into a grid and predicts bounding boxes and class probabilities directly from the grid. It excels in efficiency and simultaneous handling of multiple objects within an image. YOLO's streamlined process involving grid division, bounding box, and class predictions, and non maximum suppression makes it ideal for quick and accurate disease detection in apple leaves. So, the project strategically leverages various YOLO versions, including YOLO V5, V6, V7, and V8, to benefit from continuous advancements and improvements, ensuring a comprehensive and versatile approach to disease identification. Now we'll see the comparison graphs. So first we'll see the comparison graphs of the algorithms built for classification. So this is the horizontal bar graph comparing accuracy scores of different algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph on x-axis, I have F1 scores and on y-axis, I have algorithm names. So F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for classifications. Now we'll see the comparison graphs of the algorithms built for detection. So this is the precision scores comparison graph. In this graph on x-axis, I have precision scores and on y-axis, I have algorithm names. So precision measures the accuracy of positive predictions, representing the ratio of true positives to the sum of true positives and false positives. This is recall scores comparison graph. In this graph on x-axis, I have recall scores and on y-axis, I have algorithm names. Recall assesses the model's ability to capture relevant instances, calculated as the ratio of true positives to true positives and false negatives. And this is MAP scores comparison graph. In this graph on x-axis, I have MAP scores, that is mean average precision scores. And on y-axis, I have algorithm names. So MAP evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. So the algorithm which is best performing in all the performance metrics will be used for detections. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is data folder in which I have images of 4 different class labels for training the models and testing the performance of the models. This is sample folder in which I have images of 4 different class labels again, on which we will make the classifications and detections. This is static folder. So this folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is classification Jupyter source file and this is detection Jupyter source file. So Jupyter source file contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file Explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link. Click on it. So if we are new users, we have to register first. Fill in all these details and click on submit button to register. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password and click on submit button. So we have logged in. So here we can see a prediction link. Click on it. So as I mentioned earlier, we can perform both classification task and detection task in this project. So first we'll perform the classification task. Click on it. So here we have to upload any image. Click on choose file button. So from sample images folder, I'm selecting the first image and click on open. So the image is loaded. Now click on upload button. So this is the uploaded image and here we can see the classification, that is apple leaf is diagnosed with black rot disease. So we'll try again, click on try again link. We'll try giving another image, click on choose file button. So this time I'm selecting this image and click on open. So the image is loaded. Now click on upload button. This is the uploaded image and here we can see the prediction, that is apple leaf is diagnosed with cedar apple rust. We'll try again, click on try again link. Click on choose file button. So this time I'm giving this image and click on open. So the image is loaded. Now click on upload button. This is the uploaded image and here we can see the classification, that is apple leaf is healthy. So similarly, we can upload any apple leaf image and can get the classifications. Click on try again. Click on choose file button. So this time I'm selecting this image and click on open. So the image is loaded. Now click on upload button. This is the uploaded image and here we can see the apple leaf is diagnosed with cedar apple rust. Now click on try again. So now we'll detect, click on prediction link, click on detection link. We have to upload the image here, click on choose file button. So this time I'm uploading this image and click on open. So the image is loaded. Now click on upload button. So we can see the application has detected the diseased leaf and it has drawn a bounding box around it and we can see the classification, that is black rot. And we can also see a probability score here telling us how confident the application is about the detection and classification. Click on back, we'll try again. Click on choose file button. This time I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So we can see the application has detected the diseased leaf and it has classified the disease as black rot again. And we can also see the bounding box drawn around the leaf and we can see the probability score telling us the confidence level of the detection. Similarly, we can upload any image and can get the detections. Now click on sign out. So the conclusion here is the project marks a significant stride in leveraging cutting edge technologies, including deep learning models and YOLO based detection systems, to address critical challenges in agriculture. By integrating these advancements, we enhance disease detection precision and empower farmers with effective tools. The project's comprehensive exploration of various deep learning models from well established architectures like VGG19 and ResNet 152 to lightweight alternatives like MobileNet V2 and custom deep CNNs demonstrates a commitment to finding the most suitable solutions for classifying diseases in apple leaves. And the adoption of YOLO, that is, you only look once for disease detection, as an extension, showcases a commitment to real time and accurate identification of diseases in apple leaves. Utilizing multiple YOLO versions, including V5, V6, V7, and V8, allows for flexibility and adaptability to diverse detection challenges. And the extension of the project to include a user friendly front end with Flask and SQLite integration demonstrates a practical approach. Enabling user testing with image inputs and presenting outcomes through the front end ensures that the developed models are not only technologically advanced but also user centric. So, the project contributes to the broader goal of agriculture sustainability by revolutionizing disease detection in apple plants. The accuracy and efficiency achieved through advanced models benefit farmers, fostering increased yields, informed decision making, and ultimately enhancing global food security.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.